Welcome back. So in the last video we talked about a simple example in which two balls or two particles collide with each other, in which the initial mass, the first mass had some velocity, and the second mass was initially at rest, and the two masses moved in some direction. So we found that that was an elastic collision. So we found from the conservation of momentum we found one equation, from conservation of energy we found another equation, and we solved those two equations to find the velocities and the directions of those masses at the final instance. So in this example we'll take the same masses, but in which the masses do not collide elastically or do not collide inelastically. So this is a system in which some energy is conserved, but not all the energy is conserved, or not all the energy is not conserved. So this is not an instance in which these two masses do go as one object, in which that's an inelastic collision, or whether these two objects go elastically. So this is in between those two. So if I take the same masses, so I've been given like this, right? So I'll take the first mass as 2 kilograms, second mass as 4 kilograms, 4 kilograms, and the velocity of this mass to be 5 meters per second. And these two objects collide each other. So in the last video also I told you that the impulse and the impulsive forces are equal, so I draw that. I'll take the mass, the object which has mass 2 kilograms as A, and this object as B. So these two objects collide each other like this. This is 2 kilograms and this is A, this is 4 kilograms and this is B. So they have the same impulse, or impulsive forces actually. So I can tell, I'll take the velocity of the first mass as v1 and the second mass as v2, and I'll consider that both masses travel in the same direction, and it is in the direction in which the first mass was traveling before collision. So it will be like this. This is 2 kilograms, right? So this has velocity v1, so this has velocity v2, this is 4 kilograms, and if we are given that the coefficient of resolution was 0.75, E equals 0.75, so this is the sum, E equals 0.75, we have to find the velocities and the directions v1 and v2. So we were not given whether this is an elastic collision or an inelastic collision, but we can tell that if E is equal to 0.75, E is normally between 0 and 1. So if E is equal to 0.75, this is neither an elastic collision or an inelastic collision. But since we have given the value of E, we can solve this equation. Now, considering that the two forces are equal, we can say at any instance the total external force on this system is 0. So if the total external force on this system is 0, we can tell that the momentum is conserved. If the momentum of this system is conserved, we can say that the momentum at the initial instance is equal to the momentum at the final instance. So we can tell Pi equals Pf. So we can also take Pi equals Pf like this. Sigma I equals 1 to n I equals sigma I equals 1 to n mi. So this is at the initial instance, this is at the final instance, right? Sigma mi vi from I is equal to 1 to n at the initial instance is equal to sigma I equals 1 from 1 to n, 1 to n, mi vi final instance. So what is meant by this is, we can tell if I is equal to 1, m1 v1, if I is equal to 2, m2 v2, I is equal to 3, m3 v3, so like that up to n, mn vn. So we can calculate the total initial momentum of the system up to n types of masses and n types of velocities, and that should equal similarly to the final momentums. So that's a simple definition. This is one. So actually what we are doing is Pi equals Pf. So you can tell now from the conservation of linear momentum that the initial momentum is equal to the final momentum. So the initial momentum is only due to the velocity of the 2 kg mass, because the 4 kg mass is initially at rest, right? 2 kg, it has a velocity of 5 meters per second. So the initial velocity, initial momentum will be 2 kilograms times 5 meters per second, which is 10 kilograms per meter second. So this is 10 in this direction, right? 10 in this direction, and the final velocity of A, this is A and B. Final velocity of A, which is 2 kilograms, I have taken as V1 in this direction, and final velocity of B, which is 4 kilograms, V2 also in this direction. So they may be sometimes, as in the last problem, maybe V1 may be on the V1 may be going to the opposite side, or V2 may be going to the opposite side. So that depends upon the direction in which they are traveling. So we have to find out that, we have to solve these two equations and find out. So the final momentum of this system is 2 times V1 plus 4 times V2. So since both are in the same directions, they will add up. So it is 2 times V1 plus 4 times V2 in this direction. So this is 2V1 plus 4V2 in this direction, right? 2V1 plus 4V2. So since both the velocities we have marked in this direction, we can equalize these two without changing the signs, whether it's positive or negative. So 10 equals 2V1 plus 4V2. This is equation 1. Now we have been given that E is equal to 0.75. So we know the definition of coefficient restitution. E is actually equal to minus E is equal to V2 minus V1 divided by, this is 0 minus 5, right? Minus E is equal to V2 minus V1 divided by 0 minus 5. So V2 is equal to the final velocity of B, minus the final velocity of A is equal to minus E times the final velocity, initial velocity of B minus initial velocity of A. So that's the definition of coefficient of restitution. If you have not watched that video, watch my video on conservation of momentum in elastic collisions, coefficient, what is meant by coefficient of restitution. I invite you to watch that video and come back, because it will be easy for you to understand this concept. So however, this minus E is equal to V2 minus V1 divided by 0 minus 5. So 0 minus 5 is minus 5. So this one will become a minus 1. That minus will cancel to this one. So E is actually equal to V2 minus V1 divided by 5. So we have been given that E is equal to 0.75. We can substitute it directly. 0.75 is equal to V2 minus V1 divided by 5. Right? 0.75 is equal to V2 minus V1 divided by 5. So we can get a simple equation for V2 minus V1. We can multiply this one by 5. So 5 times 0.75 is 3.75. So this is 3.75 equals V2 minus V1. So this is equation 2. Now we have two equations. 3.75, this is 3.75 is equal to V2 minus V1. This is equation 2. So we have two unknown terms, we have two equations, so we can solve that. Alright, so to solve that, we have here minus V1. If we can make this something like in the first equation, we have 10 equals 2V1 plus 4V2. So what we can do is we can multiply this by 2. So we will have 2 minus 2V1, and we can add up this equation with this equation. So minus 2V1 to plus 2 and V1 will cancel out. We can find the value of V2, and then we can find the value of V1 by either substituting to equation 1 or substituting to equation 2. Alright, so what I will do is I will multiply 2 by 2. So 3.75 times 2 is 7.5. This is 2V2 minus 2V1. So this is equation number 3. So I will add up 1 and 3. Equation number 3, 7.5 equals 2V2 minus 2V1. I will add up 1 and 3. When I add up 1 and 3, my 2V1 will cancel. Here this is plus 2V1, and here this is minus 2V1 will cancel. Here I have 4 plus 4V2, and here I have plus 2V2, so that will be 6V2. I have here 10. Here I have 10. and here I have 7.5, those two will adapt to 17.5. So 17.5 will be equal to 6v2. So 6v2. So we can say v2 is equal to 17.5 divided by 6, right? 17.5 by 6. So this will be equal to 12, 55, 9, 54. So 2.9 meters per second approximately, right? 2.9 meters per second. So you can substitute the value of this one because you don't have to actually multiply it by 4 and then take it to the other side and divide by 2. You can easily substitute it to this equation. v2 minus v1 equals 3.75. So you know that 3.75 is equal to v2 we found 2.9 minus v1. So v1 is equal to 2.9 minus 3.75, which is equal to minus 0.85. So this is another instance, but in this instance, another instance in which the direction of the velocity changes, but in this instance, as opposed to the last video, actually the velocity of the first mass changes. Velocity in which the initial momentum was not equal to 0, the mass which is 2 kilograms, so A, that mass velocity changes, and B's velocity, or the 4 kilogram mass's velocity, stays in the same direction. So it will, what actually happens is, the velocity of A was initially 5 meters per second, and the velocity of A, the final portion was minus 0.85. So what happens is actually the direction is changed, so the final velocity will be 0.85. So what actually happened is that since the mass is constant and the velocity is decreased, we can say that the kinetic energy of A has been decreased, and since B was initially at rest and B has achieved a velocity of 2.9 meters per second, we can say that the kinetic energy of B has increased. So this is another scenario in which the kinetic energy of A has increased and kinetic energy of B has increased. So what actually I was going to, my intention of this video was to explain you how we can use, if we are not given whether it's an elastic collision or an inelastic collision, if we were given the value of the coefficient of restitution, how we can easily calculate the final and initial velocities and how we can apply the conservation of momentum. So in this video I talked about the coefficient of restitution. So in another video I will talk about more concepts or more examples in conservation of momentum. So thanks for watching this video, and I will see you there.